Hey guys, welcome to another video. In this one, what we're going to cover are rotation examples. And as you'll see, this will kind of be like a good synopsis of what we've done all semester, but with rotation as the backdrop rather than linear or translational motion. So we'll start with unit conversion, learn how to do that stuff, to kind of, cope with all the different types of units there are with rotation. There's a lot, right? There's revolutions, there's radians, there's degrees, there's all those different ways to talk about it. We'll also do some kinematic type of questions, just like with linear motion, how we did kinematics. And then we'll talk about force questions and torque questions. Then we'll go into energy and momentum. Okay? So to start things off, what we'll do is we'll do this question. So it's just a unit conversion question here. And it's a bike rotates 4.5 revolutions. And if it does that, how many radians has it rotated? Okay, so let's get started. So if you remember with unit conversions, what you do is you set up kind of dimensional analysis, but you need the conversion factor first. Well, if you remember from the previous lecture, one revolution equals 360 degrees in degree form, and then in radian form, that was 2 pi radian. Okay. So if we set up our conversion right here, we have 4.5 revolutions. Okay. And then you put the conversion factor on the bottom, or you can put one revolution on the bottom, okay, canceling out the revolution there. Then you put 2 pi radians on top. That way, revolution cancels because we're dividing it, and we'll multiply by 2 pi. So this actually equals 9 pi radians, but if you do want a number with this, you can get that as well, just by multiplying by 3.14. The number for that would be 28.3 radians. Okay. So either of these are acceptable answers. And so on an exam, I would maybe include both. Just depends. Okay, but they're both correct. So this next one is also a conversion question, but it's a conversion question that is actually kind of cool because it talks about, this particular type of bird. We're not told what it is, but birds are told to have really good eyesight. And so in this example, we'll see just how great their resolution is. So a bird's eye can distinguish objects that subtend an angle no smaller than 3 times 10 to the minus 4 radians. We want to know what is that in degrees. So we're going to use this conversion factor again, okay, to do just that. But this time we're starting in radians and going to degrees. So 3 times 10 to the minus 4 radians. We're going to do what I put that conversion factor in, but this time we're going to have radians on the bottom. And then we're going to have 360 degrees on top. That way we convert to degrees. So 3 times 10 to the minus 4 times 360 over 2 pi. And what we get with that is a relatively small number, 0.017 degrees. Okay, that is really small. So birds have pretty high resolution. Okay, or this particular bird does. Okay, so now that's kind of how pretty much all unit conversions work. As long as you know the conversion factor, you're usually pretty good. So the next one has a lot going on with it, okay? But it's a good introduction to our first type of kinematic question with this. So a carousel is initially at rest. At t equals 0, it is given a constant angular acceleration, alpha equals 0.060 radians per second squared, and that increases its angular velocity for 8 seconds. And then at t equals 8 seconds, we want to determine all of this stuff. So we want angular velocity, but then we want a bunch of linear terms, okay? So if you remember with rotation, there were, with rotation, the angular stuff, like this would be maybe like your rate of rotation around here. and that's your rotational acceleration, but you can also have your linear velocity, which would be the velocity that's tangent to this, but you could also have, if you're looking at this, you could also have a linear acceleration, and also the super important centripetal acceleration, right? That center seeking, that's what centripetal acceleration actually stands for, center seeking, caused by the centripetal force, which pulls the object inward. And so you can kind of have all of that stuff. So that's kind of what this question is going to be asking for, a bunch of those different things, okay? So we have angular velocity that wants, linear velocity, tangential acceleration, centripetal acceleration, and then total acceleration. Okay, we'll kind of go through all of those. But what we want to do, oh geez, I'm losing it. What we want to do first is pretty much what you want to do with most types of kinematic questions first. Maybe do another zoom in. Oh, too far. Is you want to start with knowns and unknowns. So, like with translational motions, start with knowns and unknowns. This helps you arrange the data or the information presented in the question. And so it's a really good problem-solving technique, okay? That kind of just carries over. And what I'm going to start with is just like with translational motion, I'll start with position, and then go through position, velocity, acceleration in its angular form, then do time, and then I usually like to do the linear terms next if they're needed in the question. Otherwise, I just kind of don't bother including them. And so if you remember, with initial position, you can usually choose it in a question unless it's defined. And even then, you can move everything back. So for this one, what we're going to do, I don't see anything about position mentioned there, is we're just going to go ahead and just write 0 radians. So this, you choose this, okay? And I choose it to be 0. That way it will cancel when we're dealing with it. Final position, there's nothing really mentioned about that, so it's technically an unknown. So we don't know anything about that. Our angular velocity, we're not told anything about, and in fact, part A, we're trying to find that. So our initial angular velocity, sorry, that's an unknown. We're trying to find, and we don't know anything about that. Our final angular velocity, we also know nothing about. Okay. So we went position, velocity. Now we go to acceleration, alpha. So alpha equals 0.060 radian per second squared. Position, velocity, acceleration. Now we do time. And remember, you can start time at 0 usually. That's usually what I always do. You can start it whenever, as long as you have the same time interval mentioned. Here the time interval is 8 seconds. So you could have 10 and 18 or 30 and 38. But why not just have 0 and 8? It's kind of the easiest to do. Okay, so after you do these are all our angular terms. Oh, a carousel initially at rest. Whoop, kind of messed that up. That means that our sorry about that, guys. We do know that's what happens when you read too fast. We actually do know our initial, this guy, 0 radians per second, because it's at rest. Look at that. that right there is a trick. Not really a trick, it's just, information that usually carries over from translational motion, right? We would do that all the time. If something's at rest, your initial velocity is at rest, or your initial velocity is 0. But anyway, I'm looking at this. We've done all our angular terms. Now we should do linear terms because it's asking for them. So the first linear term that's kind of mentioned here is the radius, 2.5 meters from center. That's what that represents, is the radius. And from here, the stuff it wants, linear velocity, tangential acceleration, basically all the types of linear terms it could ask for. So it wants this, we don't know, that's our linear velocity. And then we have 3 types of acceleration: a tangent, centripetal acceleration, and a total. And all of those we do not know. Okay? So that's our entire knowns and unknowns list. So now what we need to do is we need to go through and actually start solving stuff. The first thing it wants is we want the angular velocity of the carousel at t equals 8 seconds. Okay, so step 2, pick equations and solve. Okay, so part A, I'm going to go through. This is an equation that works because we want omega final. This is 0. We know alpha and we know time. So we can just literally just go through and just, that guy's 0. Our alpha is 0.060 radians per second squared. Our time was 8 seconds. Just make sure, 8 seconds, 0.060. You go through and you multiply that, and you get 0.48 radian per second squared. A second cancels here, you're left with radians per second. Cool. That's part A. Nice. Part B, it wants the linear velocity of the child. And so if you remember, the equations for linear to rotational terms was r times the rotational term usually. So v equals r omega. And so r was 2.5 meters. Omega was what we just found, 0.48 radians per second squared. And this will give us 1.2 meters per second. And now I know what you must be thinking. Oh, sorry. I don't know why I wrote second squared there. I know what you must be thinking. Isn't this technically a meter radian per second? Yes and no. Radian was basically a ratio of 2 lengths, and so it actually is dimensionless. It has no dimensions of anything. We give it the term radian just so we know we're talking about rotation. But we can safely get rid of it since we're talking about a linear term now. So you could write meter radian per second. It would maybe confuse you. But there's no need because we're just talking about a linear velocity. So yes and no. As you'll see in various books and things, they'll freely add and get rid of radian as their need, basically, as they need it to. Little confusing maybe, it's just kind of what you have to deal with. So the child's tangential acceleration is up next. And so a tan equals, what do you guys think a tan was? What do you guys think that equation was? If you said r alpha, you'd be right. It's kind of like I said, it's just r times the next term. And so this would be 2.5 meters times the alpha, which is 0.060 radians per second squared. You're going to have the same type of deal with the units here, where it's not meter radian per second squared, really, it's meters per second squared because we're talking about a linear term. And so that's 0.15 meters per second squared. Okay. Next up on the list is AC. And if you remember the equation for that, that was v squared over r. And so our v that we found was 1.5 meters, or 1.2 meters. Square that, and then it's 2.5 meters for the radius. And we get 0.58 meters per second squared. Next up, we had total. And if you remember, with rotation, our centripetal acceleration is this vector, or our tangential acceleration is this way. Our AC is this way. And so our total acceleration was just a combination of those two vectors. And if you remember how you do total acceleration, is it's going to be the square root AC squared plus A tan squared, right? So we're going to go through 0.58 squared plus our 0.15 squared right there. And so we get 0.60 meters per second squared. Okay. And so that's kind of how this problem works. They're going to work all the same way. Some might be, more challenging because it's kinematics, right? Or maybe you have to use multiple equations and such. But you're going to do the same thing each time. Start with knowns and unknowns. This problem was fairly consistent with radians the whole time, but you may need to convert back and forth, which you'll see in the next problem. And then just make sure you're using the right equations. Okay. So the next problem is going to be this problem involving a centrifuge rotor. So the centrifuge rotor is accelerated from 30 seconds from rest to 20,000 RPM. So now we're dealing with even another unit, revolutions per minute. But let's keep reading. What is the average angular acceleration, and through how many revolutions has its centrifuge rotor turned during its acceleration period if angular acceleration is constant? Okay. So what we need to do here is we need to deal with something, we need to deal with the frequency, okay? And so to deal with the frequency, well, first things first, let's do our knowns and unknowns, okay? So we don't know, let's see, starting with angular position, we don't know how many revolutions, okay? So we don't know that guy. We do know the initial position, as always, okay? We're going to have to go through a bunch of stuff, so I'm going to, because revolutions is listed, I'm going to write revolutions because that's how many we ultimately want, so I'm going to use the revolution for that guy. Angular velocity. So we're starting at rest. I made that mistake before. I won't do it this time. Okay. And again, we don't know anything about the unit here yet, but one thing is typically your omega value will be in radians per second. If you're talking about frequency, it will be revolutions per second. So if it's a frequency, it's in terms of revolutions. If it's omega, it's less than what a revolution typically is. Okay, so that will be in radians per second, and you'll kind of see what I'm going to do there. Omega final, we don't know either. This is what we need. What is the, we need this to find, you'll see, the average angular acceleration. And what we're going to do, you'll see how we find that guy. But we don't know it right now. And then, of course, what is the average angular acceleration? We don't know. Okay? We do know time. Time is 30 seconds. Okay? You can have t initial, t final if you want. But we're going to do 0 and 30. Okay. So, if you remember, we ultimately need this and this. Ultimately need. So alpha Well, first of all, if we ultimately need, I'll start at the very end. So theta final is all this stuff, right? So we're going to need alpha for that. So alpha then, because these guys are 0. Alpha is the rate of change of omega over time. Need omega final. So we're not given omega final, but we are given that omega equals 2 pi times the frequency. So we're actually given, I should have written this down, but we're actually given a frequency in this problem, right? So 20,000 rev per minute. That's what RPM means, revolutions per minute. So we're given a frequency, and we need to convert it into a radians per second, preferably. Okay, so to do that, we just plug into the formula here. So omega equals 2 pi, and this 2 pi is our radian per revolution. That's what its units are in this formula, radian per revolution. Our frequency is 20,000 rev per minute. Okay. So this will give us an answer that is in radians per minute. Okay, so the revolutions will cancel. We'll be left with radians per minute. And what I get when I do this is 125,663.7 radians per minute. But we need, because our time's in seconds, we need rad per second. So we're going to set up our unit conversion right here. And in 1 minute, there are 60 seconds. And so this equals, when you do that, 2094, can't write, 2094.4 radians per second equals omega final. Okay. So now we've got this guy. Now what we can do, now that we've got that, what we can do is we can find our alpha. So alpha, so now we can get alpha. So alpha is the rate of change of omega over time. So we plug all those numbers in. Over 30 seconds. This will give us to us in radians per second squared. Okay. And my number is 69.4 radians per second squared. Okay. Oops. Okay, so now we have alpha. So now we can use alpha up here to get our total, and this is our average angular acceleration. Cool. It doesn't say what it needs to be in, so we can just call it that. But we need through how many revolutions. So to get revolutions, we need total distance in radians first. So theta final equals theta initial plus omega naught t plus 1/2 alpha t squared. Gone, gone. Whoops. 69.4 radians per second squared times 30 seconds. What we end up getting is 31,416 radians, but we need it in revolutions. So we convert, okay? Okay, So 31,416 radians. And if you remember, it's 2 pi radians per one revolution. And if you divide that out, that equals 5,000 revolutions. Okay. Or 5 times 10 to the 3, but I haven't followed sig figs this entire problem, so there we go. So 5,000 revolutions is our total amount. So this problem is really, because you have to go from revolutions per minute, which is a frequency, to radians per second, then back to revolutions. It's really an exercise in conversion with a little kinematics on the side. I know there's a lot there. It's a little bit straining, but make sure when you're doing this, you're really good on what units you have. And if you're always keeping track of your units with this stuff, which is super important because there's so many different types, you should do okay. Okay. So the next type of problem we're doing is another kinematics one. There's a lot. This chapter of the book really focuses on kinematics. So there's quite a few questions. So it's a bike slowing down uniformly from v equals 8.4 meters per second to rest over a period of 115 meters. Each wheel and tire has an overall diameter of 0.68 meters. We want to determine all of this stuff: the angular velocity of the wheels, the total number of revolutions, so we need to keep track of the units again. Each wheel rotates before stopping. The angular acceleration of the wheel, okay, and the time it took to stop. So let's do our knowns and unknowns. Like always, if you're doing kinematics, you're always going to do this. For the most part, it's extremely helpful in problem solving. All right. So we're going to go through our angular quantities, so angular position, angular velocity, angular acceleration, and time. Then we'll do our linear quantities. So our initial position, I'm going to set it at 0, and I'm going to do it in terms of radians because I think that's the most helpful. Our final position, how far we've traveled, it tells us actually that the bike is slowing down to rest over a distance of this 115 meters. This 115 meters is a linear distance, but it does relate to our angular distance. We just need to do the equation, but that will be, we'll do that soon. So we don't know our final distance yet, but it'll relate to it through the radius. Omega, we actually don't know our initial omega. If you see here, so a bicycle is slowing down uniformly from this linear speed. So it's the same deal as our linear position here, but it will relate to it. So v equals r omega, right? So we'll do that to figure this out, but we don't know it right now. Our final angular velocity, though, is 0 because we're coming to rest over this distance. So we'll start at something and then slow down. Our angular acceleration, wait, do we know that? No, we need to determine it. Sorry. So that's one of the things we need to determine. And we need to determine the time it took to stop. So we don't know how long this is taking place. The next thing we need, so if you actually look here, each wheel and tire has an overall diameter of 0.68. If I'm getting diameter, I'm just going to convert it into my head, or in my head instantly, to radius. The radius is diameter over 2, so the radius here is 0.34, which is half of 0.68. Next up, we have our linear terms. Okay, so we have our x distance. We have this, our v, which is our linear velocity. And do we have an a? No, we don't have any of the a's, but we actually don't need the linear accelerations for this. Okay, so that's kind of everything. We can go ahead and get started solving now. So we need the angular velocity of the wheels at t equals 0. So we need, so part A here, we need omega 0, and that can be VR. So the relationship here, so find omega 0. So the relationship here, V initial equals R omega initial. Okay, so it's V R times omega. So since we need omega, it would be the initial velocity, the initial linear velocity over the radius. So this is 8.40 over our 0.34 radius. Whoops. Okay. And again, this will give us units of 1 per second, but since it's dimensionless, we can just convert that 1 into radians. So what it looks like is 24.7 radians per second, where it's actually 1 per second, but we throw a radian on there to know that we're talking about angular velocity here. Okay, so 24.7 is what you get when you divide that out. Next up, so part B was finding the total number of revolutions each wheel rotates before stopping. So we need the total number of revolutions. So we need theta final in revolutions. Okay, so not radians. So the relationship there is very similar to the relationship here. You have the linear term, R, the angular term. So this would be R theta. Okay, so theta final, I should write x final there, will be x final over R, which is our 115 meters, over our 0.34 meters right there. And when we do that, we get the, again, dimensionless term here. This would be just 338, but we write radians because we're talking about angular distance. Look at that 4, that looks good. The curve. Okay, so now we need to convert this to radians. So in revolution, this would be 338 radians. And then it's 2 pi radians in 1 revolution. So you multiply that and you get 53, or divide that out, sorry, 0.8 revolution. Okay. So part C, the angular acceleration of the wheel. So part C, part C is we need alpha. Okay. So the angular acceleration of the wheel here, if you remember, alpha equals the change in omega over time. But the problem with this is we don't know time. We do know the change in omega, but we don't know time, we don't know alpha. So we don't know, or don't know time. So we can't use the trick that we used before. Instead, there's another formula we can use that uses the position instead of time, which is omega final squared plus, or equals omega initial squared plus 2 alpha, or 2 alpha theta. That's final minus initial. And so what we can do here is we can solve this guy for alpha. So our omega final is 0 because we're going to rest. So omega initial squared, and remember this is outside because we're subtracting this quantity over, this should be a negative term. So we're actually putting that outside of the parentheses. Okay, and that will give us a negative acceleration, which is what we want. And our change in position here, we're going to do this in radians. So we had 338 radians right here for a change in position. And so what we actually get then, well, because this guy was 0, And so this equals minus, and then what we got for our, it was 24.7 squared over 338 radians, because this was in radians per second squared, or radians per second, and then the whole thing squared. And if you do that out, you actually get minus 0.902 radians per second squared for alpha. Okay? So that's our angular acceleration alpha. And the last thing we need is the time it took to stop. At this point, there's a lot that we can use for that. I'm just going to use part D, time. I'm just going to use what we were going to use before, the change in omega formula. There's other ones we can use. This is one of the simplest ones. Use this because this guy goes to 0. So we get minus omega over alpha equals t. So it's minus 24.7 over minus 0.902. Some radians per second squared. This is in radians per second. This will give us units of time and positive time. 27.4 seconds. Okay. So again, the main thing here, being consistent with units. As long as you do that, you go through, you do all your knowns and unknowns, you should be able to do these. Okay. All right. Let's do the next one. So now that we've done all the kinematics, it is actually time to start doing rotational force questions. Okay. So we're going to learn all about torque, and some of the torques and things like that. So the first question we have is, the bicep muscle exerts a vertical force on the lower arm of 700 newtons to lift an object. So you're just lifting an object, and it's like this. Okay, so you're lifting up as you're doing it. It's kind of hard to show on the camera. So exerts a vertical force on the lower arm of 700 newtons to lift an object. Assuming the muscle is attached 5 centimeters from the elbow, calculate the torque about the axis of rotation through the elbow joint. So what it's going to look like is, you've got your, this is actually a really poor arm, I guess. This is actually terrible. It's a drawing. So you're lifting something, and here's your axis of rotation at the elbow. Most of the time, a problem like this would be accompanied by an image, but I'm not good at drawing, so here we are. And we're exerting a force upward. So this is 700 newtons force, and this is our R, equals 0.05 meters. Okay, so these are perpendicular, so 90 degrees from each other. And we want to calculate the torque through the axis of rotation. Okay. So the torque, the magnitude of the torque, because we simplified the cross product formula, it's just RF sine theta. Sine theta here actually reduces to sine 90 degrees, which is the angle between R and F. This guy ends up being just 1. So the torque in this instance is just R times F. So we do 0.05 meters times 700 newtons. Okay, and this gives us 35 meter newton is the convention for that, for our torque. And so, yeah, if you were to write this as, this is just the magnitude of the torque. It doesn't really say in this particular instance what the direction is. With the way it's written, the way it's drawn here, this would give us a negative torque. So but clockwise, okay, rotation yields negative torque by convention. And counterclockwise rotation is positive torque. And this torque, remember, is perpendicular to both, so it will be into the page or out of the page, depending on what you're talking about. Clockwise is into the page, counterclockwise is out of the page. But again, we're not really doing anything with right-hand rule this time or direction too much. So you just need to know if it's positive or negative torque, and you can do that with the rotation. If you get into physics 2, you'll start doing more with this, okay? Because there's another thing that uses the cross product there. But yeah, that's just this problem. Pretty easy, right? You just multiply. And then if there was sine theta, you've got that. So let's do another one. Two small weights. Okay, so let's blow this up size-wise. Two small weights of masses 5 and 7 kilograms are mounted 4 meters apart on a light rod. This rod right here is our mass can be ignored. Okay, so this is telling us how to distribute the mass. We want to calculate the moment of inertia, I, for this system when rotated about an axis halfway between the two masses and when rotated 0.5 meters to the left of the 5 kilogram mass. So remember that the moment of inertia changes depending on how mass is distributed. Okay, and the equation you want to use for it also changes. So for this particular problem, so I'm going to draw it for you. These will usually be drawn for you, or you'll know the equation you use to calculate it. Here's our light rod. We have two masses. This is scenario 1, 5 kilogram, 7 kilogram, and it's rotated in this direction. Okay. And they're located 2 meters each from the axis of rotation, mounted 4 meters apart. Scenario 2, scenario. Scenario number 2, so our first mass is going to be there. Our second mass is going to be over here, so this is 7 kilograms, 5 kilograms, and it's 0.5 meters to the left of this one, and then 4 meters there. Oh, that's 3.5? Oh, 4. Wait. Yeah, because they're 4 meters apart. Yeah. Cool. So these are our two scenarios, and you're going to see how, so this will show you how I changes, so it shows how I changes based on distribution of mass. Okay. So for the first scenario, So number 1, for this system only, for this I will equals the sum of mr squared, okay? So it will change depending on how you're doing it. So this would be equal to mass 1, R1, plus mass 2, R2. Mass 1 is 5 kilograms for the first scenario, okay? And it is 2 meters from the axis of rotation. I forgot to put this and label it as an axis. Okay, so it's rotating about these points. Doesn't matter the direction in this instance. So 5 kilograms, and it's 2 meters apart, okay? Oh, forgot to square those because they're squared. And then 7 kilograms, and it's also 2 meters. So you add that up, 20 kilogram meters squared. So that's 4. 4 times 5 is 20. Here, it's going to be 4, so 28. The unit is kilogram meter squared. And this equals 40 kilogram meters squared. Okay, so that's scenario number 1. Scenario number 2 is, again, you're going to use this formula, but it's for this type of system only. Okay, again, it changes based on the type of system, distribution of mass. Like, there's a reason it said light rod with no mass. If you have a rod has its own moment of inertia. Sphere has its own. Cube has its own. So we can do m1 r1 squared plus m2 r2 squared. The 5 kilogram mass was only 0.5 meters from that. And then the 7 kilogram mass is 4.5 meters from that axis of rotation. Okay, because it's 0.5 away. This one is 4.5 away. Okay, so it's however far it is from the axis of rotation. You multiply these numbers. And remember what the moment of inertia represents. It represents your resistance to rotation. So notice here the 7 kilogram one being super far from the axis of rotation makes this a huge number. Having something farther away from the axis of rotation increases its resistance to rotation. It makes it require more force to rotate something. Okay, so this is our answer, and again, just increases I, which increases resistance to rotation, which increases force required. That is, my handwriting just progressively got worse. Which increases force required to rotate. And that force required to rotate would be the centripetal force. Okay. But yeah, massive number between the two. You have the same masses. They're just, if you distributed them evenly, they're easier to rotate. So, okay. So now what we're going to do is probably the hardest type of question you can do, maybe, or at least one of the hardest you can do with this sort of stuff. So we're going to have a, so a 15, here we go. So a 15 Newton force is applied to a cord wrapped around a pulley of mass. So the pulley itself is going to have mass in this case, of 4 kilograms and a radius of 0.33 meters. The pulley accelerates uniformly from rest to an angular speed of 30 radians per second in 3 seconds. And if there is a frictional torque of tau equals 1.1 meter newtons, determine the moment of inertia I of the pulley if the pulley rotates about its center. So what this kind of is if you remember Atwood's machines, okay, where we would have, two things on a pulley like this, and if it would move this way, this would cause this pulley to rotate. And before, we had a massless pulley, so when we were summing the forces, it wasn't a big deal. But now, if we give this guy mass, which we have here, we have to account for the torque, and then that influences the angular acceleration of the pulley, right? So it's got acceleration now, which influences the acceleration of the objects themselves. And so that's kind of what this problem is going to be about. So the first thing I would do is just draw it. Okay. So what we're going to do, so we've got this is our pulley, and we've got a 15 Newton force. Okay, let me draw that a little bit further away. All right, it's wrapped around a cord, pulley of mass, so this guy has a mass of 4 kilograms, and a radius of 0.3 meters. Kind of hard to read there. Okay. And let's see if I can blow this up. There we go. And if there is a frictional torque, so a frictional torque would mean a torque that's pointing, or at least a frictional force here that's producing, since it's frictional torque, it will be torque in the opposite direction, so our force would be applied in the opposite direction. So I'm going to write that as frictional torque. The torque isn't in this direction, but the torque is going to produce something that's out of the page, or into the page of the opposite direction. But we'll illustrate it like this. So this would be some frictional torque right here. And so, right, so that's our frictional torque, and then the pulley accelerates uniformly from rest to an angular speed. Okay. So we want to determine I. Okay, so we need I. Well, torque, net torque equals I alpha. Okay. So we need torque net and we need I and alpha. Okay. So I, what we're solving for, torque net over alpha. So let's go ahead. We need to solve for, we need both. So let's go ahead and solve for torque net first. Torque net is going to be composed of torque of the 15 newtons plus the frictional torque, or in this case, minus the frictional torque. Torque of the 15 newtons is going to be RF sine theta, where this is, again, 1. And this is the 1.10 right here, meter Newton. So RF was 15 newtons times 0.33 minus the 1.10, and I actually get 3.85 meter Newton for the torque net. The next thing we need is alpha. Okay, so now alpha. So alpha was the rate of change of the angular velocity over time. And this guy was given to us in 30 radians per second in 3 seconds. Which would be 90, or 10, sorry. Multiplied instead of divided, so 10 radians per second squared. And so now, so to solve this problem, I used the work backward strategy, which I've employed before, where you just look at what you needed at the end was I, know what you need to get those, and then you can solve. You can also do knowns and unknowns here if that would have helped you, since there is a little bit of kinematics. And this actually gives us units of kilogram, which comes out of the Newton. This ends up being unitless, so we have the kilogram meter, and so like you can kind of see where this comes from, but the seconds cancel outside of the Newton because it's a meter per kilogram meter per second squared, right? And so the second squared cancels. And we're left with these units, kilogram meter squared, which is the unit of moment of inertia. Okay. So looking back at this, you just do the work backward strat. And what you can do with this type of problem as well, or notice, again, you can do the whole, you can do knowns and unknowns and things like that. But I think work backward is the best. But you may notice that we were given the mass here. It's not relevant in this part of it. Like you don't really need to know the mass was 4 kilograms. But it could be essential in a future problem. It just wasn't in this one. So the next two problems that we're going to talk about involve the centripetal force. And so let's kind of look at how those will look. Okay. So there's a couple here that I'm going to do. We could do a lot over this. As always, you can always go deeper into something. So in this example, a 1,000 kilogram car is going around a curve on a flat road of radius 50 meters at a speed of 15 meters per second. We want to know if the car will follow the curve or will it skid if the pavement is dry and the coefficient of static friction is 0.6, or if it's icy and the static friction lowers to 0.25. How this will look, if you remember, I've said this a million times, you have something that's rotating, okay? You need something that causes that rotation. So if this guy is going around this way, you need something to cause that rotation because his velocity is this way. And then you have a force that's pulling inward. If it's like a ball on a string, like a tether ball, this would be tension causing it. For the example that we're looking at now, it's actually a car going around a turn, and it's going to be static friction that will cause the centripetal force. So what this is we've got flat ground, we've got this guy, and we've got a car, okay? And it's the force of friction that's providing static friction, because static friction with the wheels, that's pointing inward, that's actually causing this car to rotate, okay? And so we're kind of going to draw inspiration from when we were doing force examples, where we have, we've got our normal force, we've got the force of friction pointing directly inward, and we've got gravity that's pointing down. And so if we do our x and y equations here, our y equation is really easy. Normal force minus the force of gravity is 0 because it's not accelerating up and down. And our x equation will look like ma, but it's centripetal acceleration because it's moving in a circle. And ac was equal to mv squared over r. And so this will be the equation. Force of friction equals mv squared over r. By the way, for this type of problem, our coordinate system will just be the standard Cartesian system. because not only are we following the force of friction, but more importantly, since our acceleration, the center-seeking acceleration, centripetal acceleration, is towards the center of the circle, we want to follow that, okay? So I've said it before, but I'll say it again. You want your coordinate system to usually follow where your acceleration ultimately lies. And so for, incline problems, right, our acceleration was down the incline, so we tilted the coordinate system. Here, our acceleration points towards the center of the circle, so we'll have a coordinate system that looks like this, which gives us an equation that looks like that. And we want to know if the car is going to follow the curve or if it will skid. Okay. So first of all, what we need to do is let's look at the requirements. So let's look at how much force is needed to move in a circle at this speed. Okay? So the needed requirement, you have a 1,000-kilogram car, 50-meter radius, and 15 meters per second. So the force needed is mv squared over r, which equals 10,000, or 1,000, sorry. I was like 10,000, that's a lot. 1,000-kilogram car. It's actually kind of small, I think. Or maybe it's typical. 15 meters per second squared over the 50 meters for the radius. And this yields 4,500 newtons on average to keep this going. So that's the force needed. So now let's look at what the coefficient of static friction will be with 0.6. Okay. So the coefficient of static friction, okay, is equal, if you remember, to mu s, because we're talking about static friction, so it's the coefficient of friction times the normal force, which in our case, the normal force is equal to gravity. It's mu s Fg, and then the force of gravity is mu s mg. So the force of friction for the dry case, oops. So this is for dry. Here, let me write it like this, so I don't have subscript on subscripts on subscript. So dry case is 0.6 times 1,000 kilograms times 9.8. And that is 5880 newtons. So this is above the 4,500, so this is good. So check above 4,500 newtons. This will not skid. Okay. And then it wants to know for the dry as well, or for the icy as well, at 0.25. So we'll do the same thing for icy. So force of friction static for icy is 0.25 times 1,000 kilograms times 9.8. And this gives us 2,450 newtons, which is not good enough. So this is below 4,500 newtons. And so it will skid. Okay, so as expected, it will skid on icy surface. I mean, that's what ice does, right? It lowers the coefficient of static friction, which will make it skid. All right, let's do another problem with this type of setup. And again, on your homework, you may see stuff with like a tether ball. In that case, it's the force of tension causing rotation. But friction, like I said, can cause it too. If you're looking at maybe maybe you're doing like a roller coaster or something and you're spinning around a roller coaster, it'd be the normal force that's providing your, because you're in a seat and it's pointing towards the center, your centripetal force. But for these problems, it'll all be friction, or we'll see. Okay, so this example actually is going to use normal force. There's a version of this that uses static friction as well, but let's look at this one. So for a car traveling with a speed of 14 meters per second around a curve of radius 50 meters, we want to determine the angle at which a road should be banked so that no friction is required. So I don't know if you've ever really noticed, but on the road, especially like exits or places where your speed is changing rapidly and you need to go around a corner, you'll see that the curve is banked, which means that it's rotated. And the reason it rotates, or the reason they bank a curve, okay, is because what happens is you saw on the previous example, it was all friction that provided this rotation, or the force needed to do the rotation. With this setup here, the more you tilt it, the more the normal force contributes here. So banked curves are banked, so there's less reliance on friction to provide centripetal force. Okay. So they're like this just so you don't have to fully rely on friction to basically be able to go around a corner, right? So if there's ice, maybe you won't go skating. So the free body diagram for something like this, because we want to know, for a car traveling 14 meters per second around a curve with this radius, determine the angle at which the road should be banked so that no friction is required. So we're assuming that there's no friction at all needed. So our free body diagram would be this. We have the normal force, okay? And we're banked, so this would be where the bank was. And so, yeah, this is just our free body diagram. If we had friction required, we would have friction pointing along the incline downward, but we don't, because we just want to know what it's like without friction. And again, what I'm going to actually do is I'm going to do this setup for our x coordinate system and our y, our Cartesian system, simply because we want the acceleration. So A of c will point this way, again towards the center of rotation. Okay, so our x and y equations will look like this. So Fn, the angle's right here, so it'll be Fn sine theta because the angle is right here, so that'll give us, sine will give us the x. And this will be equal to mv squared over r. F of g is fully in the y. So we have Fn cosine theta, which points up, minus f of g pointing down. Okay, so cosine, that cosine is right there, pointing up. We have f of g pointing down. And that's equal to 0, because we're still not moving up and down. We're going to be moving at the exact same place, height-wise. And we want to know what's the angle. So we need to solve for theta. So let's solve y for f of n first, because we have two equations, two unknowns, theta and fn, so we need to solve for fn in one. Solve fn in y, plug into x. Okay. So fn cosine theta minus f of g equals 0. So Fn cosine theta equals f of g. We just divide now, so f of n equals f of g over cosine theta equals mg over cosine theta. Okay, so the other equation was Fn sine theta equals mv squared over r. We're going to take this guy and we're going to just plug it in there. mg sine theta over cosine theta. So there's our mg cosine theta, or mg over cosine theta times the sine theta equals mv squared over r. We can cancel m's. So we get g sine theta over cosine theta. So we're solving for theta, so we need to divide by g. Now, sine theta over cosine theta, this is actually tangent of theta. So we can go ahead and just write tangent theta. And now we want to solve for that angle. So theta equals the arctangent of v squared over rg. So it's the arctangent of, it's been a long problem, so I don't even know where we're at, 14 meters per second. So we're going to square that guy over 50. So this is squared over 50 meters times, okay, and this actually equals about 22 degrees if you plug that in. Okay, so that's the angle required to not have any friction. So again, these two that we just did, these are more similar than these two together are more similar to like the Newton's second law stuff, and so a lot of people do put them in there. I usually keep it with the rotation section. I go back and forth on it, but I do think since we're talking about rotation, it makes sense to include them here. Okay, but that's basically forces. So you'll talk about, you'll have torque, you'll have moment of inertia I, you'll have that's those sorts of questions, and then net torque. Okay. Next up, we've got rotation, or we've got energy. Okay, so we're talking about energy and momentum for the last two sections of rotation. So we want to know what will be the speed of a solid sphere of mass m and radius r when it reaches the bottom of an incline from rest at a vertical height h, and it's rolling without slipping. So let's look at this. So we've got this type of problem. And remember, this is an energy conservation question. And so since it's energy conservation, you need to do energy initial and energy final. Okay, so energy initial, energy final. This is in no way the same shape. Let me move this down. So use energy conservation. And this type of question will work very similarly to the past one. Where where you just need to figure out the energies at the different points. So what we have here is we have a height h. So what we would usually do is the energies in EI would be m, or big M, because that's what I called it. You'll notice in physics, whenever you're talking about things with solid amount of mass, you'll use a big M. When in other parts of physics, like we've done up until this point, before rotation, you would use a tiny m, because it's just a particle. So you've got big M, G, big H. And energy final, right? This guy would just be moving, and it would just be 1/2 m v squared, right? So you'd have some linear motion. And we'd be trying to solve for that. So at the end, it would have kinetic energy. At the beginning, it would have potential energy. But there is one other thing that it now has. It has rolling energy. Okay, so it'd be plus 1/2 I omega squared. So it has, at the beginning, because it's starting from rest, only gravitational potential energy. Now, here, let me use a different color. Now it's got, at the end, it has kinetic energy plus rolling energy, okay? So it will work, this type of problem will work the same way. You're still going to just add up everything and set it equal. But there's a couple things that you need to consider when you're doing it. So because of, so here, let's do it this way. Next, set EI equal to E final. Okay. Okay. So this is it right here. But because we don't know I or omega, we need to do some stuff. So we need to rewrite I for a solid sphere equals 2/5 mr squared, where this is the radius and this is the mass. Omega is equal to v over r. And so what we're going to do is we're going to plug this in. So and again, I think I mentioned this before, I will usually, if you need this on an exam, I will give you I, big I, okay? I will give you everything you need to solve for that. So let's go ahead and rewrite mgh plus the linear kinetic energy. Now we're going to add over the 1/2 I. So for I, it was 2/5 mr squared. And now omega is just v squared over r. But since it was omega squared, it's v squared over big R squared. Now what you'll see is there's m's, well, here, let's rewrite, let's multiply all of this out, simplify it a bit. Two tenths mr squared v squared over r squared. These can now cancel, as can the masses. Just like before in energy conservation problems, you can usually cancel the masses unless you're dealing with springs. Okay. So now what we need to do is we need to solve for v, because that's what we need. We need the speed at the bottom. We need to make this common denominator, so times 5. So this would be 5/10 v squared plus 2/10 v squared. 7/10. Now we just need to multiply over, so it'd be 10/7 on the other side. And we just take the square root. So v equals 10/7. And this is our answer, because we don't know what g is and we don't know what h is. We're just given this terms in terms of just generic variables. So yeah, this is one type of problem that you could get if you had, if you had something other than a sphere rolling. You had like a rod or a cylinder or something else. It would have a different moment of inertia I, which would change how it rotates. But you'd be given what that is. But the math would work similarly. So it's still energy. You just have to incorporate all types of things that are there. So in this case, we only had potential energy, and then kinetic energy and rolling energy at the end. But if you had springs and stuff like that, you'd have to incorporate that as well. Okay. So now the last type of problem that we're going to cover is a conservation of momentum question. Okay. So we've done everything else, and this is the last question for this lecture. So a non-rotating cylindrical disk, this will tell you about the moment of inertia, okay, but it's given in terms of I, so we may or may not need that later. So a non-rotating cylindrical disk is dropped onto an identical disk that's already rotating at an angular speed omega. And we want to assume no external torques. What is the final common angular speed? So what's happening is we have a P initial and a P final. So you use constants of angular momentum. Okay. So we have a disk here, and this is omega equals 0, so non-rotating, and it's dropped onto omega equals something, angular speed omega. Okay, cool. And then in our final, they're together. And they're rotating. Or that doesn't have a rotation. That has a rotation. And so we want to know omega final equals what? So let's call this omega 1 and omega 2 initial. And then we want to know what is omega final. And they'll be combined. So a non-rotating disk is dropped onto that is rotating, and we want to assume no external torques. What is the final? So this is kind of similar, where you would have one cart that's moving and it would bang into another one that's not moving. And then we saw the fallout of that, right? Where it's based on the masses and things like that. So, oh, I used the wrong symbol for angular momentum. It's L for angular momentum. So our initial rotating thing. It's just a non-rotating disk. Okay, so our initial is actually 0 because we're starting with non-rotating. Okay, we're just looking at this guy. Our final whoops, hold on, sorry, I messed that up. So we have the non-rotating plus the rotating, omega, which I called omega 2 initial. Okay, so this is the non-rotating. Our final is they're combined, so they'll have double their moment of inertia for a disk times omega final. Okay, and so set our initial equal to final, just like before. So you have just I omega over here, which we've called 2, 0, or 2 naught. And then over here we have 2I, 2 times the moment of inertia times omega final, because they're rotating together. The i's in this case will cancel, so we actually don't have to worry about what the moment of inertia is. It's just like when the masses cancel, right? Because moment of inertia is basically the angular equivalent of mass. Mass is resistance to linear stuff, and angular momentum's resistance to rotation. And so now we have this. And so our final velocity is just our initial rotating over 2. So it's half the angular speed because we can't write, but it's because we doubled I, our moment of inertia. Okay, so we doubled the angular mass, okay, and that halved the speed. Okay, just like it would if we were doing like regular momentum with a cart. So anyway, that's all of the examples I have for this, for rotation for now. Thank you all for watching, and I'll see you in the next one.